Well, all right, everybody. Good morning. Very good to see everybody here. How's everybody doing today? Doing all right? Oh, okay. Seeing enthusiasm. Okay, very good. So today we're going to be thinking about nuclear power. That's what we're going to be focusing on. So over the past couple of weeks, couple of lectures, we've been thinking about atomic physics. We've been thinking a bit about nuclear physics. And today, we're going to be seeing how those concepts can be applied to actually do something useful for us, so to generate energy in the context of nuclear power stations. So we're going to be understanding a bit about the physics of how this works. We're going to be seeing the most famous equation in all of physics. And we're also going to be seeing how this actually applies in the context of a nuclear power station. So we're going to be thinking about nuclear fission, and also about nuclear fusion. So hopefully lots of interesting things to be thinking about today. Now I'd like to start with a picture that's got some connection to what we're thinking about. And today I've got this great picture here from the Sizewell C construction site. So they're constructing a new nuclear reactor at the Sizewell nuclear power station. Over the course of you guys' careers, this is going to be one of the biggest employers for physicists, for engineers. If you're really thinking about something which might have some real connection to what you guys might be doing in a few years, this really is an option. They're going to be hiring a lot of physics and engineering graduates. Before we dive into the physics of this, I'd like to get you guys' opinion. So I got this question here, and we're actually thinking a bit about nuclear power stations, and I'm really curious to hear what you guys think about nuclear power. So maybe do you think we should expand nuclear power, be building way more nuclear power stations? Maybe we shouldn't be expanding them, maybe we should be maintaining them at current levels. Maybe if you're not such a fan of nuclear power, maybe we should be thinking to reduce them. Or maybe if you're really not a fan of nuclear power, maybe we should eliminate them, turn them all right off straight away as soon as possible. So I'm really curious to see what everybody thinks for this. I'll just get the question going, and then we'll see what everybody thinks for this one. With this question, there's no right or wrong answer. Certainly don't worry about getting this correct or anything. I'm really just curious to see what everybody thinks. So maybe you might want to have a chat with the people around you, see what they think. Maybe they agree, maybe they've got a different point of view. But it's just really interesting to see what everybody thinks about this one. Well, all right, great to see all of those responses come in. Let's take a look. Let's see what everybody thinks. I'm really curious about this. Let's have a look. Okay, oh wow, so nobody's going for D. Not so many people going for C. Looks like, wow, we're really going for A, expand, okay. Wow. I'm really, that's really curious. Okay, well, thank you all very much for putting your response in. That's great to see there. So who voted for option A? Who's the kind of really we should be expanding nuclear? Okay, wow, so quite a lot of people. So what are some of the reasons you guys are thinking about expanding nuclear power?
It's just cleaner, and I think if we expand, then we get away from fossil fuels.
Right. So cleaner, move away from fossil fuels. Okay, what about some people over here? Are you thinking about expanding? Yeah, what do you guys reckon? Yeah, Joe? Oh, sorry? Because it's cleaner? Okay. Does anyone have any other reasons why they want to expand nuclear power? Any other thoughts about that? Okay, and what about the people who voted for maintaining nuclear power? Okay, so maintaining it at the current levels. What's your thoughts about that? Why do you reckon we should be keeping it at current levels but not expanding?
I don't want to add any more to the radioactivity that it's producing. Like, although it's efficient and it's good and it's better than fossil fuels, it's still dangerous.
Okay, yeah. All good points. And what about option C? Does anybody want to chip in some thoughts why they might have gone for option C? Okay, now that's fair enough. I mean, it does look like people are going for option A. So today we're going to be learning about some of the physics involved in nuclear power, and it'd be really interesting to see what you guys think, once we kind of delve into this. But that's really curious. Okay, so thank you all for putting those responses in. That's great to take a look at that. Okay, so let's start by thinking a little bit about how we go about, getting some energy out of an atomic nucleus. So we saw a couple of lectures ago, we saw nuclear equations. So I got a example of a nuclear equation here. So suppose we've got two deuteriums, so an isotope of hydrogen. So we got one proton and then the neutrons there. And suppose we combine them together. So which of these options could be a product that we get when we do this nuclear reaction? If you're not sure about this one, remember that with any nuclear equation, we have to have the mass number being the same and the atomic number being the same. So take a look at what the combined mass number and the combined atomic number going in is going to be. Whatever the nuclear product is going to come from this, it's got to have the same mass number and atomic number. So have a look at those possible options, see which one of those could fit those requirements. All right, very good to see those responses coming in. Let's take a look. Let's see what everybody thinks. What could we get here if we combine the two? Okay, so looks like most people going for option B here. Some people thinking it could be all of them. Now, these can be a bit tricky, especially, we've got like this beta minus going on here. And, we've got some neutrons here. But it's really simple. If you just break it down, it really is like kind of basic math. Even I can manage to do it in my head, okay? So let's see how this works. So the atomic numbers. Now, this is going to be like the easiest math you are going to see for like your entire time at university. So do just take a moment to appreciate like how nice and easy the math involved in this question is, okay? So let's start by thinking about the atomic numbers, okay? So we've got atomic number of 1 over here. We've got atomic number of 1 over here. So 1 add 1, it's going to be 2, okay? So the atomic number in the product, it's got to be 2. So if we have a look at the options here, so 1 minus 1, that's not going to work for us. 2 minus 1, not going to work. 2 add 1, that's going to be 3. So we can kind of narrow it down. And then also we can think about the mass numbers. So again, 2 plus 2, it's going to give us a mass number of 4. So 3 add 1 is going to be 4. Okay, so it has to be option B. Okay, so very well done, everybody who got that. It's option B. And like I said, make sure you give a bit of practice with these kind of questions, because if there is something like this on the exam, they are really, really easy if you know what to look out for. You don't even need to get your calculator out, but just make sure you know what to be looking out for. Okay, so very well done, everybody, with that we got option B. So if we have two deuterium nuclei and we fuse them together, what we're going to get is we're going to get one of these heliums over here, and we're going to have a neutron left over. Now, this is actually a very important reaction whenever we're thinking about nuclear fusion. So we know what the decay products of this reaction are going to be. Now, this is where it gets a bit more interesting. Let's take a look very closely at the masses involved in this reaction. So let's have a look at what we've got here. So we've got the mass of the deuterium, so slightly more than 2 in these atomic mass units. I remember an atomic mass unit, you can think about that, it's about the mass of a proton or a neutron, but we've been really, really exact here. So we've got that mass of the deuterium. So we've got 2 deuteriums going in, and then we get the helium-3 coming out, and then we get the neutron coming out. Now, I know I'm always saying, don't use too many significant figures. 2 or 3 significant figures is enough. But just this one time in this question, it's really important to be thinking about all of the significant digits involved here. You probably will need your calculator for this one. So have a look at what goes in. Have a look at what comes out. Let's take a look. What's the mass difference that we have left over in this reaction? With this one, we really are just calculating the combined mass of what's going in and then subtracting the mass of what comes out and seeing what we're left over with. All right, very good to see those responses coming in. Let's see what everybody thinks for this. What's the mass difference? How much mass do we have left over here? What's the missing mass? Okay, so nobody's going for A or D. Looks like most people going for B. So when you add up twice the mass of the deuterium that is going in and then subtract the helium and the neutron, what we're left over is this mass difference. What should we get here? Option B. Okay, so the correct answer is option B. So very well done, everybody who gave this question a go, especially if you got that it's option B. But this is kind of really curious, right? That what's coming out is not the same as what's gone in. Okay, we get this mass difference left over. Does anybody have any thoughts about what's going on here? Where's this mass difference come from? And where's it gone? Yeah. Yeah, exactly. It gets turned into energy. Okay. Any other thoughts about this? Exactly how much energy we're going to get? So you might think not too much energy, okay? Because so 1 atomic mass unit, very, very small unit of mass. So if you were curious to see exactly how much energy we get, so we're going to need to convert, that atomic mass unit into maybe kilograms. And then any thoughts about how we can work out how much energy we're going to get from this reaction? How can we go about calculating that? Any thoughts? E equals mc squared, absolutely right, 100%, okay? So, most famous equation in all of physics, okay? So we get a mass difference, and we can work out how much energy with E equals mc squared. Now, I had a look around, and as far as I can tell, this is the very first time that this equation was written down. So it's from one of Einstein's famous papers from his extraordinary 1905 year, where he just had this extraordinarily prolific series of papers and really changed modern physics. And the paper, I won't try and murder the German, but it basically does the energy content of a body depend on its mass. So if we have a look here, even if we're not kind of fluent in German, we can have a look, the energy. So they use an L for energy instead of an E, but energy L. So equal mass of L over V squared, and he's using a V squared instead of C squared. So V for the speed of light. But this is the paper that introduced this concept. Okay, so it's originally written as really mass is equal to energy divided by C squared, which clearly didn't seem to be as catchy as E equals mc squared. But this is the equation. This is where it's come from. So whenever we have a nuclear reaction like this and we have a mass difference, we can use E equals mc squared to calculate exactly how much energy we're going to have. And we're going to have lots of examples of this in the workshop. So do make sure you give these a go, because they're quite simple calculations, but there's lots of kind of extreme numbers all over the place. So do make sure you give those questions a go in the workshop. So this is the basic idea of what's happening to that mass difference, where's it going, how much energy we're going to get. Let's take a bit of a look at some of the physics involved here. So what we have on this axis of the graph, on the vertical axis, is we have potential energy. So we've seen this a few times before, especially when we were looking at, the Coulomb force. We have the force between two particles, but we also have the potential energy. And then on the horizontal axis, we've got the distance, so how much these two particles are separated by. So you can think about this, maybe we've got one proton over here, and then we're trying to push together another proton. Now, if the two protons are kind of fairly separated and we try and push them together, so we've got two protons, two positive charges. So if you remember when we're thinking about the Coulomb force, we're going to get that repulsive force. They're not going to want to go together. So it's going to be pushed back. And the way you can think about this, it's a bit like if you're trying to push something up a hill here. So this potential energy gives us some idea of how much resistance the particles are going to get when we're trying to push them together. But if we keep on pushing and then we reach the top of the hill, then it's going to fall down and it's going to feel this very strong attractive nuclear force, and they're going to get pulled together. And this difference in potential energy between when we're trying to push them together and it's feeling the Coulomb force and this really deep, as we say, potential well when they're pushed together, that's where that mass difference is coming from. So that's a kind of basic sketch of what's going on here. But what really is going to influence if we're going to be able to get energy out when we push something together, or we're going to need to split something apart, it's really due to where the element is on the periodic table. So what I've got in this graph, so on this axis, we've got the number of nucleons in the nucleus. So what we have here are all the elements of the periodic table. Now, this is quite a complicated graph, quite a lot of things going on here. So let's just take it step by step and break it down. So over here, we've got hydrogen, so just hydrogen 1, just one proton, and then hydrogen 2, and then hydrogen 3. So some of those isotopes that we've just seen. So we have more nucleons in the nucleus. As we keep on adding these particles to the nucleus, what we see on this vertical axis, so it says average binding energy per nucleus. So depending on exactly how we've assembled our protons and our neutrons in the nucleus, so exactly how many of them we have, that's going to affect the energy that each particle is bound together with. And then it's divided by the total number of particles so that they're all on the same scale for us. So as we keep on adding more and more, we can see that the binding energy per nucleon increases until we get up there, Fe56, so until we get up to iron, which is the most stable element, okay? So if we have a look at what's going on here, we've got iron, it's got the highest binding energy, and it's the most stable. But if we look over here at the other side, so this is the far end of the periodic table, you know, we've got uranium-238, uranium-235. These are really unstable radioactive elements, and they have a lower binding energy per nucleon than iron. So if we're over at this side of the periodic table thinking about really heavy elements, we can split these elements apart, and that's going to release the binding energy. And that's what's going on with nuclear fission. So because they have a lower binding energy than iron, anytime we split them apart, we're releasing some of that mass difference, and we're moving up towards lighter elements until we get to iron. And then same kind of idea if we go over to this side of the graph, if we're looking at the light elements. So if we start with hydrogen, if we combine those elements together, as you guys saw with the deuterium example, that releases energy, so that mass difference you saw. And that's fusion. And the reason fusion energy is difficult and why we don't have fusion power stations at the moment, if you remember that chart of the potential energy, there's that big Coulomb repulsion as we're trying to push these together. So you have to get these particles really, really close before they snap together and they release that binding energy. So does anybody know where we do see nuclear fusion occurring? Any thoughts about that? Yeah, the sun, exactly right. See it in the sun. So stars, okay, so this is the physical process that powers the stars. So stars are going to start out with very light elements, mainly overwhelmingly hydrogen, and they're going to fuse them together, move up the periodic table until they get to iron, and you can't get any energy out of iron, okay, because it's the most stable. And then one way or another, the star's going to end its life. Maybe it's going to go a supernova, and we're going to be left over with iron. So that's why, the core of our planet, big chunk of rocky iron. So there's a lot of physics to unpack in this graph, but this is the basic idea of what's going on with nuclear fusion, nuclear fission, and how we can release those elements. Now, before we think a little bit about exactly how this works in a nuclear power station, I'd like to share with you guys one of these physics simulations that we've seen a few times before. So let me just bring it up on the PC over here. So what we have here is we've got an example of a uranium nucleus. And if we have a look at what's going on here with this graph, we've got potential energy on this axis, and then distance between the daughter nuclei. And it's the same kind of idea as that graph we saw before, where we need to push them together and they get the Coulomb repulsion and then they snap into that attraction. But now we're thinking about splitting this uranium atom apart. So if we have a look at the potential energy of the uranium atom over here, there's some forces keeping it together. So that's the nuclear force, really strong, keeping this nucleus together even though it doesn't really want to be together. But if we split this nucleus and they get slightly further apart, then they're suddenly going to feel that Coulomb repulsion and be pushed apart really, really fast. So again, you can kind of think of this as like our uranium nucleus sitting in the bottom of a little hill, and if we shake it a bit so that it's pulled apart, each side is going to fall down either end of this hill. Uranium that we've got up here, so the uranium-235, we can actually help it to split apart if we zap it with some neutrons. So as we add neutrons to this nucleus, it becomes unstable and then it splits apart. So give that another go. So we fire the neutron, it starts to become unstable, and once it gets more split apart than that distance on the graph, then it's going to feel that Coulomb repulsion and be pushed apart very quickly, releasing that energy. So that's just with one, but if we want to get like a nuclear power station, we need to set up more of a chain reaction. So we've got the same idea here. We can fire one neutron and then it splits apart. Did you guys see how many neutrons we had released from that reaction? Did you guys see? Let's give this another go. So we put one neutron in, and then we get 3 neutrons out. So potentially, each time we have this decay, we can trigger 3 more. Okay? So if we dial in some more of these nuclei here. Here we go. Let's start a bit more reasonable. So if we just fire one neutron in, we might get some other reactions getting fired off. So we've not fissioned all of them, we've got some left over. So let's just, for fun, dial it right up to the maximum here. Here we go. So this should be quite exciting. Here we go. Okay, so it looks like we've pretty much got all of them fissioned there. So this is the basic principle whenever we want to extract usable energy from nuclear fission. So in a nuclear power station, we want to have a nice steady reaction. So we want to have one reaction per reaction. That's going to give us a nice steady source of energy. If we have a runaway reaction, like we just saw, what's that? Where are we going to find that? Any thoughts about that? So that's an atomic weapon, okay, so that's a big explosion. So we really don't want that. In a nuclear power station, we just want a nice steady source of energy. So let's take a look at how this reaction works in a bit more detail. In a lot of nuclear power stations, we might be seeing, uranium-235, and this is a sketch of the chain reaction going on there. So we start by putting in one neutron, and then we get 3 neutrons out, and then we can get this increase in the reactions. Okay, so in a nuclear power station, we want a nice steady reaction. We want one product reaction per reaction. Okay, that's going to give us that steady nuclear power. And each nucleus is going to decay after absorbing another one of those neutrons, because that's going to make it unstable, a bit like in that animation where it's kind of starting to shake, becomes unstable, and then it splits apart. So this is the particular reaction here. So we've got the uranium-235, add 1 neutron, and then we get these decay products, and we get the 3 extra neutrons. So if this is self-sustaining, we're going to get a chain reaction. So if we don't have one reaction per neutron, then the reaction's going to fade out. Okay, we're not going to get the power. If we get more than one, then it's going to build up exponentially. It's going to melt down or get an explosion. So we need to control the reaction and keep it going nice and steady. So something we can use to control the reaction is we can add neutron moderators in our reactor. We'll see a bit how that works in just a couple of slides. Now, another important point to think about whenever we're thinking about reactors, so whether that's a fission reaction or even a fusion reaction, is the reactor efficiency. And this is just the ratio of the energy that you get out of the reactor to the energy that goes into the reactor. So call that number Q. That's what we mean by reactor efficiency. So if we're making, say, a fusion reactor, we need to really heat up whatever we're trying to fuse, so maybe that deuterium, so we need to put some energy in. And if we want to make a power station, we need to get more energy out than goes in. Otherwise, it's no good for us. If we're putting more energy into a reaction that's coming out, then that's not going to work as a power station. For the last few slides of the lecture, I'd just like to share with you guys some kind of schematic diagrams of nuclear reactors. So starting by thinking about nuclear fission reactors, where we're splitting atoms apart, and then for the last couple of slides of the lecture, think about a little bit what might be going on with nuclear fusion reactors, okay? So we've got a schematic diagram of a nuclear fission power station. So like, what they're building in Sizewell C. Now, whatever kind of nuclear reactor we're thinking about, so fission, fusion, all those different types, all they're fundamentally doing is they're generating heat. And that heat is being used to turn water into steam and then run this steam turbine and turn the electric generator. So do you guys remember a few slides ago thinking about Faraday's law? We were generating that AC current. We had the person just standing there turning the coil, generating the power. All we're doing with the nuclear power station is generating heat to generate steam to turn that turbine for us. And that's true whether it's a fission power station like this or a fusion power station, which might sound more complicated, but fundamentally all we're doing is generating heat, and we want to be producing more heat from the reaction than has gone in to get the reaction started. So in a fission reactor, we really just put the fuel rods together, and if we bring them close enough that we get that reaction going at the right rate, the fuel rods, they're just going to heat up. That heat gets transferred to the water that surrounds it, and then the water heats up, and then we use that to run our generator. Now, in a fusion power station, all that fundamentally changes is instead of putting fuel rods here, which are undergoing fission, we're going to have some situation where we are fusing particles together and using that heat to run our turbine. Does anybody know the kind of setups we might be using to get a fusion reaction going? Maybe has anyone seen any kind of examples? Have you guys seen anything? Okay, so for the last few slides, I'd like to share with you guys the two main types that physicists are thinking about to generate artificial fusion reactions, okay, to get that energy out of fusing two deuteriums together. And I'd actually like to share with you guys a couple of my favorite examples from the movies, which are actually surprisingly accurate and kind of really kind of interesting examples of fusion at work, okay? So I got this slide here from Iron Man, so the original 2008 movie. How many of you guys have seen the original Iron Man 2008? It's such a great movie, right? I think it's one of the best of the Marvel ones. So the idea is, we've got Tony Stark here, and he becomes Iron Man because he figures out how to make a fusion reactor that fits in his chest. But it's based on what he calls, this arc reactor that he has back in Stark Industries. And, you can see the plasma swirling around there. Now, you might think, okay, Marvel, there's kind of quite a lot of artistic license. But this is actually a really pretty accurate example of a real-life design for a fusion reactor called a TOKAMAK reactor. I think TOKAMAK, it's based on like Russian for kind of donut, because that's the shape of the reactor. And when I saw this, I was like, wow, okay, that's actually really pretty accurate there. They really got everything about right. I mean, in real life, you don't have transparent walls, but aside from that, it's pretty accurate. So this picture here, this is what a real TOKAMAK looks like. This is a composite picture. So here we've got the plasma, and this is when the reactor isn't running. And I don't know, what do you guys give them out of 10 for accuracy? I'd say pretty good, right? So that's a nuclear fusion with a TOKAMAK reactor, where we've got it kind of donut shaped. Now there's another main kind of artificial fusion reactor. So another way that we can really heat up plasma, get it hot enough that we can extract energy from it. And amazingly, another really fun example I can share with you guys, it's also from another really good Marvel movie. So this one here is from Spider-Man 2, so the Tobey Maguire Spider-Man 2. Who's seen this movie, right? How many? Oh, not so many. Okay, look, for my money, it's the best Spider-Man movie, okay? I really think it's a brilliant movie, absolutely fantastic movie. So if you haven't seen it, the idea is we've got Dr. Octopus here, and he's constructing a fusion reactor. That's why he kind of turns into Dr. Octopus. And what's going on with the reaction here is that he's got the fusion products, so this could be some hydrogen, and it's in this confinement here, and he's blasting lasers at the hydrogen, using that to compress the hydrogen, heat it up, and undergo nuclear fusion. Now you might say, okay, Spider-Man 2, really not super accurate. But when I watched this movie, I was like, wow, that is actually really pretty accurate. Okay, let's take a look at the real-life equivalent. So this is the National Ignition Facility in the USA, and this is the real-life experiment. So they put the nuclear fusion fuel in the center here, and then they hit it from all sides with lasers. And I think I've got to give them credit in Spider-Man 2. It's really pretty accurate. Clearly, they've taken a bit of artistic license, but the fundamental principle, they got it right. So whether you want to learn about tokamak reactors or inertial confinement fusion, the two main kinds of fusion, I could highly recommend either of those two movies. Now, last thing I'd like to share with you guys for today. So you might think, with the Dr. Octopus, and he has to get the robot arms, okay? So the idea was that in the movie, he needed to attach robot arms to himself in order so he could go in and control the nuclear fusion stuff without getting his body in the fusion. Now you might say, okay, that really is, stretching things into the kind of fantastical regime. Surely you don't need robot arms when you're doing nuclear fusion. But the last thing I'd like to share with you guys today is actually a picture from inside the jet fusion reactor in Oxfordshire. And as you can see here, they really do have robotic arms to go inside and fix up the reactor. So even, one of the most fanciful elements from Dr. Octopus, there is some grounds for reality in there. So just before everybody packs up and heads off, just a quick reminder. So we've got the bank holiday on Monday, so no lecture on Monday. Next lecture is going to be in a week's time, okay? But we are going to have the workshops on Tuesday. So I hope everyone has a great weekend. If you want to do any, studying nuclear fusion, please do. You can think about watching Iron Man, Spider-Man 2, learn about diffusion from that, okay? Chalk it up as physics revision. But that's it for today. I hope everyone has an excellent bank holiday weekend, and I'll see you guys next week.